nothing new, and the grades are pretty good. So now today we're in antennas, and if you're asking about the average, I think it was a little over 7.2 maybe out of 10, but I don't have that in front of me. There are plenty of perfect data. So now, what I wanted to do, I was trying desperately to do this on Friday. I want to get down to, if we have an antenna, we know we can get the magnetic vector potential that's fictitious. So how do we go about, from that, getting the actual E-field nature? I asked you to take, how many realized I asked you to take the curl of A to get H? Did anybody do that? Try it. Wasn't it on one note? It was. And I'm not going to go through the whole 9 yards of this, but just listen. We found that if you had a differentially long, if you had a current element I in the Z direction located at the origin, and its length was L, or I'll call it capital L, then it gave rise to a magnetic vector potential A here that was mu0 I times L over 4 pi R, right there, times e to the minus j beta R, and it would be in the AZ direction. Y'all remember that from last time? I put it AZ. I'm not going to put AZ there. What I'm going to do is put the spherical transform of AZ. And for AZ, what happens is, it becomes what? AR times cosine of theta, right? And then it's minus, really, A theta times the sine of theta, where theta is the measurement of the angle here to the R radius vector R. I'm not trying to bore you with this stuff. I just want to make sure you at least understand how come there's going to be a couple other field components. Now this vector potential A, that's fictitious. I call it fictitious. It's an abstract concept. Only the curl of A or the time derivative of A, when you add the gradient to it, have any real interpretable meaning in the real domain. In other words, the measurable domain. Now the curl of A from that will have terms. It'll have a first term, actually maybe second term, that'll be like this. It'll be J, I, beta L over 4 pi R times e to the minus j beta R here times the actual sine of theta, and it will be in the A, B direction. Now that's the first term. The reason I'm saying this is, does anybody know why I'm saying this? There's one important fact. It's really important to appreciate. You see how this varies as 1 over R? R is going to be the measure from the origin to the point of observation. Y'all follow me on that? Now there are there's one other term here. There's another term that I'm not going to put down. I asked you to do this for homework. I may actually give this as a problem and collect it for some extra credit. There's another term that will vary as e to the minus j beta R, but it falls off as not R, but R squared. So that term in there, the mathematical function and constants, are something that you determine when you take, or I'm sorry, I have curl of H, my bad. This is H, and this is actually equal to curl of A. Put it this way. H is actually equal to curl of A over mu. I'm sorry if I'm confusing. Do you remember this class? I said the curl of A was equal to H. Do y'all remember that? And divided by mu naught, that's H. This is the magnetic vector, or this is the magnetic field in amps per meter. There's another term that will vary as 1 over R squared here, and it will be in the A phi direction. Now I want to make sure I make this clear to you. This is the term that has to do with propagation. That has to do with radiation. You're going to see me emphasizing this over and over again. Are you with me, class? This term has to do with the near field energies. Do you remember I told you about near field, or I used the term, let's see, it's the energy that is associated with the non-propagating waveform. In other words, when you charge a capacitor, there's an electrostatic field around it. That electrostatic field has energy you can get back out. When you have current through an inductor, it creates a magnetic field about it, and you can get that energy out. But when it's propagating and launched, you can never get it out. Now, all propagating fields in the far field will fall off as 1 over R. They have to. I promise you that. Just remember that. So this term has to do with really the inductive energy. Now, if you went ahead and you said that, I don't know if you did this whole thing. Suppose I take curl of A over mu and I get H. So I have H is equal to curl of A over mu naught, or mu, either one. And then I want E. Well, I know curl, or let me do it this way, curl of H right here is equal to, normally it's J plus the partial of D with respect to T. You all agree with this? One of the things I didn't say explicitly yet, but it's always assumed, is we're an air or a lossless media for propagation. The reason I say this, when we talk about antennas and radiation and stuff, it makes no sense to say it's in a highly attenuating region. Why you put an antenna in a region that the signal's going to just die off to nothing? Right? So we assume it's low loss. Actually, what we do is assume it's usually a vacuum or air. So epsilon and mu are that of free space. You get curl of H here is equal to, normally it's J plus the partial of D with respect to T, correct? But here, we go to the frequency domain, and we just say it's J omega epsilon E. Now the reason we do that is because we're assuming sigma 0, right? We go to the phasor domain. Y'all follow me on this? This entire workup is in the phasor domain. Now, when I replace H as curl of A over H, I get 1 over mu curl of A is equal to J omega epsilon E. And therefore, if we take curl of H and divide it by J omega epsilon, we find that E, in fact, is given as 1 over J omega mu epsilon times, and then it would be the curl of H, and I'll just show you the vector identity. That's the gradient of divergence of H minus del squared of H. Does anybody remember that vector identity? How many do? I put it up there a couple times when I was solving a wave equation. You all remember it? Some of you do. All right, you don't have to know it, but here's the one thing that's nice about this. What do you know about divergence of H? Anybody? It's 0, right? There are no magnetic monopoles. Divergence of H is 0. Do you all agree with that, class? So this goes away, and we're left with that. And that, in fact, will be the E field. Now, there's some tricks to this, but I wanted you to understand something. If you get A as this, from a short dipole, I'm sorry, right here. Then, if you take the curl of this, and it has to be done in spherical coordinates, you're going to get this plus another term. If you went ahead and just took the curl of that H, you would divide by J omega epsilon, you get E. Or if you had H, you could do that and get E. That's a second order derivative. In either case, what you really care about, what we care about in this class, are not the near fields. Dr. Whitworth, if he teaches this, may have you do a little near field stuff. That's the stuff, the energy comes back to the antenna. What we care about is the propagating electromagnetic fields. So, that said, I'm going to erase this, and I'm going to get to the bottom line. What you need to know, why you need to know. Now, if you take a physics course, like a senior level physics or graduate course in EE or in physics, then you'll go through all the 9 yards of proofs. You'll do all of this, you'll get really familiar with gauge conditions, and you'll be very familiar with this. But right now, you're applications-oriented engineers. You need to know this, enough science and physics and stuff like this, So you can go and address a problem with the proper techniques and know what formulas apply and why they do. But you don't have to be able to recreate anything. So here, put this down. This is for a short dipole. Now we get to the bottom line. And these are going to be for propagating fields, propagating or far fields. Therefore, the electric and magnetic field a long way from the actual source. So there is no magnetic energy or electrostatic energy to worry about. You all with me on that? Now when we have this, I'll draw my little antenna here. And I'm going to say this has a current I. The length is L. And I'm at a distance, matter of fact, let me do it this way. I'll put this right at the origin. And I'll make it length L, like such. And this is going to be the angle theta. Dr. Whitworth's book always has this oriented on the z-axis and at the origin. So here's my current. As a current I, it's right on the z-axis. Y'all follow me? It's just a little chunk of current. As a matter of fact, I didn't say this here yet, but L has to be less than lambda over 10. If it's not less than that, what I'm showing you doesn't apply. Y'all follow me? We're assuming that there is almost no phase difference in the current over the length of that thing. So if we have that and we're out a distance r, what we're going to find is we're going to get a magnetic field and electric field. The electric field, this is in the far field, these are far field quantities, and this is in your book. The way Dr. Whitworth does, he gives it as J eta beta I times L over 4 pi r, and r is the range to this point. In the book, he uses a small r oftentimes to designate that range. It'll always have a phase constant of e to the minus j beta r, and it will vary as the sine of theta, and it will be in the a theta direction. Now here's what it means by that. This is some important things here. First, the relative strength of the electric field is proportional to I right there. Right? It's got the a to beta business in there. And it's inversely proportional to R. Y'all follow me? This is just the magnitude. Now that e to the j minus j beta r, that's just a phase term. Like when you have tan at an angle of 30 degrees, tan at an angle of 0 degrees, tan at an angle of 100 degrees volts, it doesn't matter. You don't care about that when it comes to the real essence of the problem, the power, right? Things like that. That's a phase. Now this is important, because what do you see happening here? Remember, this is the electric field that's propagating, launched. Well, look up here. How much power goes right up the axis? What's the angle if I'm going straight up, class? What's the sine of 0? 0, nothing, right? Nothing propagates in the direction of the current. That's an important concept. Nothing propagates straight down. Where is it a maximum? Yeah, at theta equals, say, 90 degrees, right? It peaks right here. Y'all follow me? As far as the electric field magnitude, we'll get to the power in a second, but y'all follow me? So get an intuitive appreciation for this. And here's the nice thing. If you have the E field in the far field, this is a propagating electromagnetic field, the H field can be gotten in magnitude by simply taking the E field, taking E field in the theta direction and dividing it by eta. By the way, eta is just the square root of mu naught over epsilon naught. I'll call it eta naught. And that's 120 pi ohms. You all know that? Or 377 ohms, correct, class? So the ratio of E to H, if it's propagating, is always going to be eta. Or if we wanted the H field and we had the E field, we divide by eta. Do y'all follow me? This is for propagation. This is what we're concerned about. Near field stuff is interesting. I'll level with you. If you're doing experimental work and you've got an antenna in some immersion solution, and you got a real nearby transducer, then understanding the near field values and their effects, their attenuation is important. But for everything we're going to be doing and considering, we're not that worried about it. And that's important. Now, therefore, what is H going to be? Can you all see it's just going to be this quantity right here and get rid of eta? You all see that? And then you can see it still depends on sine theta e to the minus j beta r, but it will be in the phi theta or the phi direction. It will be because it's got to be perpendicular to the E field. So it will be equal to j times beta times I over 4 pi r times L, it's got to be proportional to the length, times e to the minus j beta r times the sine of theta, and it would be in the A phi direction. Now in Dr. Wentworth's book, he shows you what I've got here. He actually goes through the proof somewhat. He doesn't do the whole thing. He does the H field proof on page 442, equation 8.46. But what he does show you is the E field I showed you in equation 850, and the H field I showed you in equation 8.49, if you want to write them down. Just so you can look at the reference in your book. All right? They're both on page 443, and you can see his workup on that. I like to have people do this. Let me just tell you my reason. If that is true, generally, there's an assumption here. You don't appreciate A and gauge conditions and all that yet. I mean, that's far beyond what this class can really delve into. But once you do, you'll see this is the entire, it'll give you both the E and H field. If that is true, then you get the entire near field included, E and H field, by doing the curve operators, all right? And that becomes important later on, not in this class, but more or less when you're in waveguides. A lot of the field's real near field to the actual antenna, and you have to have an appreciation for this to do some work. So just understand that. We're not going to touch that. So these are E and H from a short dipole. Please put down short dipole, underscore that. And these fields, and write this down, are going to be for distances. I'll just put this down here. I didn't prove this. These are going to be for R greater than lambda over 2 pi. This is called the far field parameter. Far field limit. Now he has this and he has this in equation 8.48 in his book. And this is lambda in free space. Let me just make you appreciate this. So I got a short piece of wire. I know it's a lot shorter than the actual wavelength, right? I mean, the wire is much shorter than the wavelength. So let me give you a concrete example. Suppose I'm at 300 megahertz. That's the driving frequency. And where it would be driven, I didn't show you, this would be a gap there, and just put plus or minus a voltage that's changing at 300 megahertz. Y'all follow me on this, class? What's the wavelength of 300 megahertz? Well, it's C, 3 times 10 to the 8th over 300 times 10 to the 6th, or 1 meter. You follow me on that, class? So if I take 1 meter and I divide it by 2 pi, call 2 pi 6. It's more than 6, all right? So if I have 1/6 of a meter away, I got to be more than 1/6 of a meter. So if I'm like a meter away, it's no problem. I'm in the far field. Do y'all follow me on that? Now you'll notice that this far field requirement has nothing to do with the length of the antenna. Please listen to me, right? What does have something to do with the length of the antenna is this assumption. The length has to be less than 1/10 of a wavelength. Got me on that? If it's not, then what we're doing here doesn't work. Then it's a longer dipole. But just appreciate. First, if your dipole meets this requirement, check the box. Then, to be in the far field, you have to be this far away. You with me? How many understand that? It's not hard, but you have to think about it. Okay. Next, if we have the far field there, well, I got E and H, propagating field. What else might I get? Anyone? Think about it. What do we, we're engineers, what do we like to think about a lot of, besides money? Power, right? We like to think about the power density. These are meant to be joked. Don't write me a letter. How dare you? I'm kidding. I say that only because I've been in too many board of trustees meetings and stuff. It's always about finances. I promise you, when you go to a company, anybody work for a small company or moderate-sized company? What's the big meeting of the year? The business meeting, right? Where the financials are rolled out? My gosh. If they're in the red, you're dead. That's the same. So anyway, when you talk about power, really, we don't talk about power the way power people do, because we talk about power density first, don't we? What is the average power density in a way? PAV is what? It's for propagation, it's what? Well, all right, I'll just put it down. You're right, you're absolutely, I'm going to put the formal equation, real part of E cross H conjugate, right? That's the formal way to do it. If the E field and H field are in any environment, it'll work always, correct, class? But we always break it down if it's propagating as what? 1/2 times the E, I like this form, magnitude of E squared, that's the propagating E field, squaring it. And it's a magnitude, remember. So if it's complex, you gotta take the magnitude. You don't put the A plus JB in there. That's right. Over eta, that would be the intrinsic impedance of free space or of the region. And it will be in the AR direction. So it's in the direction it's propagating. Y'all agree with that? Now, you could also say it's 1/2 times eta times the magnitude of the H field squared AR. These two are the same. Just like power is equal to V squared over R for DC, or power is equal to what? I squared R if you're talking about current, right? So these two are equivalent forms. And that's the power density, and that would be in terms of watts per meter squared. Y'all agree with that? Class? Now, that at least makes a little more, I mean, when you're talking about power density, it's something you can appreciate, right? I'm gonna break this down to something that's a lot more applications oriented in a second, but I just try to make sure you understand it, right? Now look here, if we wanted the power density for that waveform, this waveform, or this electric field, or this H field, doesn't matter which one we use. If we choose the E field, just listen to me now, I would take this quantity and square its magnitude, right? Y'all with me on that, class? All right, when I square the magnitude, that J goes away, doesn't it? Y'all see this E to the minus J beta R goes away also. That's a phase term. So I'm going to have A to beta IL over 4 pi R squared and sine squared, right? We're going to do this. I'll put the 1/2 in front first. So it's 1/2. And here I'm going to have beta beta L times I, all squared, right? Then I have 4 pi R, all squared. You with me on that? Then I have the sine squared, right? Y'all with me? Now, it's divided by eta, isn't it? I don't want to move too fast. Remember, that's just the E squared. So if it's divided by eta, can't I just get rid of one of these? There's an eta squared here, and I can just erase that and put an eta there. Can't I, class? That's just one way to do it. You don't have to do it that way. All right? With me? That's power density. Now, I'm going to tell you one thing here. There are many, many forms. If you look on the internet, or on Chegg, or whatever you use, beta is 2 pi over lambda. Y'all hear me? Sometimes it's 2 pi over lambda in there squared. Well, then there's a 2 pi squared and a 4 pi squared, right? And they'll do cancellation there. So you're going to see a variety of forms of this equation, but they'll always be current squared, length squared, proportional, and 1 over r squared. Y'all follow me in that, class? That's the way it's always going to be. As a matter of fact, what can we see happening here? Let me just do this for a second. Show you this. And this is in the AR direction. We're assuming that the actual antenna is located right at the origin in the Z direction. Please just bear with me with this. So if I have this here, I'm going to play a little game here to see how we can do it. I'm going to take a look at this stuff right here just for a second. And when I do that, I have eta over 2, and I have beta squared L squared, I squared. Then I have 4 pi squared. Then I have R squared, right? Now, the only thing I'm doing is looking at the stuff in front of the sine squared. Y'all follow me? Right? What's another way to write beta? I said 2 pi over lambda, correct? Just bear with me. You don't have to do this. You just have to follow my thoughts. So I'm going to put for beta 2 pi over lambda. And I'm going to square it, okay? Now what's another way to write eta? I mean, there's a lot of ways. Eta is square root of mu over epsilon if we want. We can leave it as eta if we want. But what you can see here happening is now I'm going to reduce this to what? Well, I have pi squared, that goes away. Correct, class? I'm just showing you how I'm thinking. I still have 4 squared, but I have 2 squared here, don't I? So that can get rid of one of these squared, get rid of that 2 and put it as 1. Correct, class? All right, now just wait a second. I think I forgot a squared operator, didn't I? Let me put it back to what it was. It was 4 pi squared. Hang on. And this is 2 pi over lambda squared. Let me do it this way. First, I'm going to get rid of the pi. I can't get rid of that lambda squared. I know that. Then, that 2 squared is 4 over 4. Get rid of that and make that 1. But it's still lambda squared. That's what I was getting at. Now, I have lambda squared and I have eta. So I have eta over lambda squared. Eta is square root of mu over epsilon divided by lambda. Well, that's c over f, right? Correct, class? For free space? So it's c over f, or I can put f here, correct? C is downstairs divided by f. F comes up. What is c? It's 1 over the square root of mu epsilon. Do you follow me on this? You can see what I'm working towards, right? What else do you see happening here? I'm sorry. I didn't do that right. This is squared. Let me do it this way. Square root of mu over epsilon over, and this is going to be 1 over mu epsilon times c over f. Yeah, so it's going to be f squared mu epsilon. I'm just trying to show you one thing here. What I'm going to get as, when I take this up here, you're going to get mu epsilons here. So what do you end up getting? Let's see here. Maybe this isn't really worth the time doing it, but I'm going to have eta over lambda squared here be equal to square root of mu over epsilon times mu epsilon times f squared it's going to be that still isn't going to get me where I want. Anyway, I'll leave it as this for now. The thing, just this whole thing right here, I'm going to redo. I can leave it as that for now. But now what I'm going to do is this integration to calculate total power. So let me erase this. So you get, this is really what I need to do to make sure you see it. Let's try to get this down to a more condensed form. What I'm going to do is say P av here is going to be equal to some constant k times the sine of squared of theta in the AR direction divided by r squared. Here, k will just represent all that business right there. It'll be beta divided by 2 times beta Li squared over 4 pi squared. And then the r squared term I'm leaving out here in the sine squared. So that's, I'm just replacing with k because I'm going to do an integration now. You with me, class? Can y'all see it in the back? All right, so that's the power density here in watts per meter squared. Now when I come over here to find total power radiated, then I find, and I'll just call this P radiated or P rad. That's what Dr. Wentworth's book has. Well, that would be the integral of the average power density over the surface for a closed surface that encloses the antenna. I'm going to write down mathematically the exact form. Did y'all follow me the concept? You take the average power density. If you include a surface that encompasses closed surface, the antenna, it has to be the total power radiated. Make sense? Everybody? Yes, sir.
And the K equation there, the R squared in the denominator.
Remember what I wanted to do? I wanted K by itself, so I have 1 over R squared. It'll be part of the equation. I just wanted to I wanted all this stuff right there to put down as a constant, so I don't have to keep writing it. That's what my goal is. So this is going to be the actual, this is the mathematical symbolism, but here's what it comes down to when the numbers are put in. So I can say P radiation from that is equal to, well, this is a surface integral, so it'll be a double integral. Do you all agree? Right, it's spherical coordinates. So first you take the power density, which is in the radial direction, which is that K, right, times the sine squared of theta over R squared in the AR direction. Now some of you might not remember doing this, but the differential surface at a constant distance R in spherical coordinates, how many remember it? It's R squared sine theta, right? You remember that? Times the, sure. So it's going to be R squared, right, times the sine of theta, right, times the phi d theta. So it's a double integral. And it's in the AR direction. The reason I'm putting that down here is because all differential surfaces, and that is a differential surface, has a vector sense to it. With me, class? It has to. An area doesn't, but a surface is a vector. So it's the differential area times the surface vector. Surface vector is AR. If you really want to know, here's my little antenna right there. I put a spherical surface around here at a range R, and then I integrate the power density through that surface to find the total power. Make sense? How many see this, by the way? You guys not see it? Or do y'all understand what I'm talking about or not? If you don't, let me know so I can help you, because this is important that you at least have an appreciation for what's going on. We got a power density. We have to integrate that over the surface the power density flows through to get the total power. If you don't appreciate that, none of this will make sense. Now, this is a surface integral in spherical coordinates. So the first integration is phi. Phi is in the xy plane. It goes from 0 to, class? It goes all the way around, right? 360 degrees or 2 pi radians. Do y'all agree with that? I'm seeing a lot of positive. If you have x, y, and z, remember, phi is measured from the x coordinate, right? So if we're doing phi integration, we're going all the way around, right? From 0, right, to 2 pi. Y'all with me? Okay, so this goes, the phi integration goes from 0 to 2 pi. Now, the vertical, what about the vertical? Well, if this is theta, it goes from 0 to pi, right? Pi radians are 180 degrees. You with me? Let me see that. It's important, really, it really is. So it's from 0 to pi radians. Now, if we're doing this integration, I want you, does anybody see what cancels right off the bat? So we don't have to worry. The R, yeah, and if it doesn't, then you made a mistake. Because the irradiated power, total radiated power, cannot be a function of how far away you are. Unless it's a lossy medium, but this isn't. So we just get rid of this R squared, thank God. Now, what do you see happening here? AR dot AR is, anyone? 1, right? Unit vector dotted into itself is 1, isn't it, class? If it was AR dot A phi, it would be 0. AR dot A theta is 0, correct? Everyone? Sure. So get rid of that. You get rid of that. Now, you'll notice the K comes out in front. It's a scalar, right? We don't care about it taken out in front. And then we're left with sine cube. So we have sine cube theta right there, and the K comes out in front. Now this type of an integral, in the past, I'd make a little more of a fuss about it, but nowadays, you have symbolic integration on your calculus. It's no big deal. I'm going to do it one time just so you see it. I won't keep on doing this. All right, here's the way I do these things. You see anything in here that's a function of phi? No, so when I integrate d phi between 0 and 2 pi, I just get phi evaluated from 0 to 2 pi or 2 pi. Do you all agree with that? How many do? With me? All right, so I'm just going to get rid of that and put a 2 pi out here. Now, to do this, do I remember your calculus tricks? This is a Jitendra Tugnage thing, right? How many have had Dr. Tugnage for college? 1? Well, he is big into trig. I mean, that's sort of, you got to know your trig identity. Say this over and over. I think it's on a shirt, right? Isn't there something like that? You got that thing on your back? Does it say that or not?
I'm just going to look at your
I trust me, if you haven't had them, you're in for a real treat. So this, the way you do this is you always, anytime you do an integration, think of a differential and the integral form. All right. If what you want is something here where you have both the differential of it and the integral form of it. Now follow me on this. Sine cubed can be broken down as sine squared times sine, right? Well, sine squared is 1 minus cosine squared of theta, then times the sine of theta. Y'all agree with that? You remember it now, probably, right? Now what am I going to do? This is EA. Thank God they won't ask you this in an interview, unless you're teaching math. When you look at this, what do? You let u be equal to cosine of theta, and du equals minus what? Sine theta d theta. Doesn't it, class? Do you remember this, the old sub-O trick? So when you do this, you get rid of this too. Are we together on this so far? You guys know this, right? Now what I'm going to do is replace the cosine with u squared. Okay? You follow me, everyone? I gotta make sure, right? So maybe I'll put it right below here. So this integral for p rad is going to be equal to 2 pi k. And then in front of here, now I have the integral from 0 to pi of sine theta d theta. I can do it that way. Or really, I can just do it this way. 1 minus u squared, sine theta d theta is going to be minus du. And I'm going to change these limits. Y'all follow what I've done there? Right. That sine theta d theta is minus du. And then I have to do this. Now, if u is equal to cosine theta, when theta is equal to 0, the cosine of theta is 1. And when theta is equal to pi, the cosine of pi is minus 1. I'll do this only once. Are you with me, class? In the back, and everybody can see this? I don't want to belabor this, but you all see there's a minus here, right? There's a minus right there. And now what happened, I mean, I could put it right here, can't I, in front? It's technically, it's a coefficient, -1, right? I can take it in front. Now what happens if you have limits from A to B and you reverse them? That's right. If I have x dx from A to B, that's the same thing as what? Minus x dx, right? From B to A. So what I do to get rid of that minus is this. Make this 1 and make this -1. Now we're cooking, right? Make it easy. And what do you see happening here? Well, I have, this whole thing becomes, let me put it up here. All right, I have du integrated is u. I'll put this down as 2 pi k. It's u evaluated from -1 to 1, right? And then for the next part, it's minus, and the integral of u squared du is u cubed over 3, right? From -1 to 1. That would be the power. Do you agree, class? So what happens here? Now I have 2 pi k. In the first integration, when I evaluate u at 1, it is 1. Minus, a -1 is 1. 1 plus 1 is 2. Right? Y'all agree with me? Then I have what? Minus 1/3. And I have 1 cubed, right? Minus what? Minus 1 cubed or plus 1, right? So now I have 2 right there, so it's really 2/3. And you can see this becomes 2 pi k. And now 2 is really what? 6/3, right? Minus 2/3 is 4/3. This is something to remember always, or try to at least. The integral, if you have an integration of sine cubed theta d theta, as such from 0 to pi, this thing will be 4/3. Just something to keep in the back of your head. You're going to see this over and over, trust me. So now I have that, and now I can get, that's the total radiated power. Do you agree, class? And if you look at the total radiated power, I substitute my k in here, and lo and behold, that's what happens, all right? I'm going to cut to the chase here. So I just wanted to show you that integration. This is it. This is P radiation right there. Let me get this off the board. So if I took K and plugged it in here, I want you to listen to me now. And you turn the crank, there are a lot of cancellations, you would find this. The total radiated power, and this is from a short dipole, would be equal to 40 pi squared, and then it would be the length of the antenna over lambda squared. Now that's in Dr. Wentworth's book, this is times I squared, pardon, times I squared. And this is in Dr. Wentworth's book. This is equation 8.55. I was trying to get it down to a point, I don't have time right now to show you how all this stuff cancels, but trust me, it cancels. If you want, I'll do it after, be in my office after 2 and I'll do this for you. Now the real thing is this is for a short dipole total power radiated. We don't care about that. You know what we care about? A thing called the radiation resistance, and here's why. We know that the power radiated in general, think back to your time when you had circuits. and you're talking about power dissipated by a resistor. That's equal to 1/2, right? 1/2 times I squared times R, but this is called the radiation resistance. And it's in ohms. Now what is our radiation? You'll notice this is just 1/2 right here. Our radiation would be double this. So now we say that the radiation resistance for a short dipole is simply 80 pi squared, and it's the length of that antenna divided by lambda squared. Got a comment about it. Y'all follow me on this? This is the real thing that comes out. When you look at that for a second, in order for a dipole to be short, L has to be what with respect to lambda? Anyone? At least a tenth of a wavelength or shorter, right? So if it's worst case, if it's a tenth, right, then this is 1/10 squared, 1/100. Y'all follow me? 1/100th, I got 1/100 times 80, so that's 0.8. Y'all follow me? 0.8 times pi squared, call it basically 9, or call it 10. That's only ohms, real low. Y'all follow me? So one of the problems with short dipoles is they have a very low driving radiation resistance. You got to put a lot of current in to get anything out, and that's not good because current means heating up of the wire, which means power loss. You would like a lot of power without much current. That's the reason your power lines have such high voltages when they carry current a long distances, because power is proportional to V times I, high voltage, low current, low loss. So same thing with antennas. We like low loss, or we like a lot of power, which means high, we want a high driving point impedance. Now, that said, I'm not going to have time to do my next thing, but I'll just tell you where I'm going. All this stuff is kind of, I don't know. It all came down to this being the radiation resistance, right? And we knew how the power. Next time what I'm going to do is take you through and show you how to get what Dr. Whitmer talks about, the directivity and gain of an antenna. And we're going to see how for any given antenna, if you know the gain, you can easily get the power density, you can get the electric and magnetic field, you can get all sorts of information. Please show up to the next class. And it's going to be much more, I'd say, into the problem domain that you'll appreciate. It won't be abstract. But I have to go through this, okay?